Yeah, now it's working. Okay, so it's all yours. Go ahead.
Thank you. So good morning once more. And in our presentation, we will move to larger objects than we discussed previously on the session. We will move to impact of hazardous objects. We will consider the interaction of objects larger of about 10-20 meters with the atmosphere, which impact could have catastrophic consequences. And these impacts occurred in past and definitely will occur in future. It is not possible to make a full-scale laboratory experiment of hazardous impacts, and detailed numerical simulation of particular case needs a lot of time. And so we, in order to have fast and reliable estimate of hazardous effects from any impact, we need some engineering model, we need some scaling relations which can describe all possible hazardous effects. And we are trying to get these scaling relations, and we implemented them into online calculator, which can provide quite fast estimate of hazardous effects in any point you are interested in. There are not only our calculator in the internet. The most famous one is Impact Earth calculator by Gareth Collins, Jamie Losch, and Rob Marcus. And it was elaborated more than 10 years ago, and the authors used the results of nuclear test to estimate, to suggest scaling relations and to estimate hazardous effects from cosmic impacts. So we decided to conduct serial numerical simulations in a frame of specially elaborated gas dynamical model with radiative transfer, which describes the interaction of cosmic objects with the atmosphere. And we do that. On the panels, you can see how the 40-meter objects evolved during its penetration into the atmosphere with decreasing altitude of flight. Our model is calculated in two steps. On the first step, we consider the interaction of objects with the atmosphere, deceleration, ablation, deformation, and pancaking, growth of instability, and transformation of object into rarefied high-velocity jet and others. And on the second step, we use the result of the first one and to conduct the 3D modeling of impact consequences. There are two main scenarios in the interaction of large objects with atmosphere: airburst and crater-forming impacts. And the impact scenario, which is realized, is determined by the impactor size, density, and entry angle. And you can see on the panels how these scenarios changed with object size and entry angles. The boundary between this scenario may be related with so-called effective altitude. And in fact, it is the altitude of the main energy deposition. And you need to determine it correctly in order to get reliable scaling relations. In fact, at large distances from the epicenter, point source approximation provides reasonable shockwave effects if this altitude of energy equivalent point explosion is correctly determined. And we suggest some relation for this effective altitude. You can see it here. We considered numerical results for more than 100 cases for objects of asteroidal and cometary nature from 20 meters to 3 kilometers in diameter, entering the atmosphere at different angles and different entry velocity. There are about half of them are airbursts and more than half are crater-forming events. And analysis of these results permit us to suggest scaling relations for hazardous effects. Here you can see the distribution of overpressure on the ground for 50 meter in size object, and numerical modeling results are shown by dashed lines and our scalings by solid lines. on the left panel. We suggest scaling relations which include anisotropy, so the effects are not equal at the same distance from the ground zero. On the right panel, we compare our scale. We compare results of our numerical simulations with the scalings implemented by Garrett Collins in Impact Earth calculator, as they do not include the anisotropy, as they used scalings from nuclear explosions, and they used pure point source approximation where we modified it, including the special heterogeneity. Of course, we need to compare our results with known events, and here you can see comparison of our scalings with Tunguska data. And on the left panel, the overpressure contours are overlaid on the map where the damage after Tunguska event is shown also. And we found that at quite large distances, about 400 kilometers, there should be some glass damage. And we did reanalysis of eyewitnesses data, and we found that really the glass damage occur in small Russian villages along the Angara River. And so results of our scaling are in good agreement for overpressure data with observational data for Tunguska. Of course, Tunguska occur in sparsely populated area where only a small camps exist, and if it occur in more populated area, it would be much worse effects. We include thermal radiation in our calculator, and in the case of air burst scenario, the main source of the radiation is bolide radiation. You can see how the bolide looks like at different altitudes. And on the right panel, you can see the thermal exposure on the ground. And for this object, 50 meters in diameter, the thermal exposure is large enough to ignite dry leaves and pine wood. And for crater forming events, much larger, the main source of the radiation is a plume, which rise up after the flight of the meteoroid. And of course, thermal exposure is much larger than cases. You can see it on the right bottom panel, and even melting of some quartz can occur in the epicenter. We suggest the following scaling relations. It's like point source, but we include some anisotropy there as well.
You have 5 minutes left.
Okay. The important parameter in radiation scaling is the fraction of impactor kinetic energy, integral luminous efficiency, and you can see dependence on energy on these two panels for small size objects, meter scale and 10 meter scales, and for larger objects. And you can see that the behavior of this integral luminous efficiency is quite complicated. It decreases, it increases, decreases, and then increases again, because you have change of the main source of radiation in this case. We also try to compare our data with Tunguska again, and there is not certain parameters for Tunguska, but there is absolutely independent modeling by NASA Ames research group published by Johnson and Stern, and we compare our prediction with their model, and you see that despite a slightly different range of impacted parameters, both models are able to describe one area, and different model results are quite close. Our modeling suggested more oblique impacts. We also include first the atmospheric disturbances which occur in the atmosphere after large impacts due to plume formation. Plumes form, deteriorate, and cause oscillation at altitudes above 100 kilometers. And this disturbances spreads over thousands of kilometers. You can see the initial plume formation on the left side and further evolution on the right side. We suggest to describe these disturbances by some parameter relative density, and it is largest in density of epicenter and decreases at the scale of thousands of kilometers. The only instrumental data on atmospheric disturbances was observed in Chelyabinsk event, and we compare our prediction with observations on this bottom right panel, and you see that both the amplitude of the disturbances and the characteristic time are in agreement. We also include and modified seismic effect into our calculator. We reconsider the seismic efficiency for crater forming impacts is occurred to be larger than was suggested before. And for airburst cases, we determine this average seismic efficiency. And here you can see how the panels, how the pages of our web-based calculator looks like. You can enter your parameters here. When you push some icons on the result page, you will get more detailed information about hazardous effects in the point where you want to see. And here you see some concluding remarks. I would like to emphasize that the first time it was special serial modeling of cosmic object impacts. We suggested first time the scalings for airburst radiation, for atmospheric disturbances, and for airburst seismic effects. And so thank you for your attention, and please use our calculator. We will be glad to get any reply from you. Thank you.